Hello and welcome to another episode on building CTFE. Today we are going to tackle the problem of string concatenation at CTFE, which also will require us to get our memory management straight. So here is what I came up with. I'm going to have a stack, and the stack is synonymous with other virtual registers you can use, and a heap. And we are going to have to specify how we are going to work with the heap. So first, what is a heap? A heap is nothing but a block of memory. You can dice up however you want. The heap is all the memory you can use, basically. So we are going to support a 4 GB heap on which we put every object, every string, everything. Except for integers, basically, on which we have to operate fast, because every heap access is going to have a penalty, a huge penalty, and because of the layout of the CTFE interpreter, this penalty cannot be avoided. So we want to use it for data, and on which we are not going to do that much math, if that makes any sense. Okay, so we are going to go in BC Common. We are going to define a heap data structure. I already started. And the first thing we want to support is to store string on the heap. How do we do that? Well, we build something that takes this const char character, which is what string expressions are when they come from DMD. They're UTF-8 strings, and we are going to push them on the heap. What do we do there? Well, we do this. We take a pointer and the size, which is constant, by the way, as well. And we are going to set our size. Let's call it heap size for convenience. Say heap size plus equals size. And before that, we could assert that heap size plus size is smaller than heap max. This shouldn't be an assertion normally, but while we are still developing, this will be fine. Actually, we should enforce that and do something when that happens, but in development mode it's fine. This is of course not all we do. Next we need to copy, which means we're going to have and we require that all strings are zero terminated. Well, I guess we can assert that. Yes, this will work. And because it's zero terminated, we can do a fast loop here. Now we have this underscore string. And then we loop through there. And say C equals and not equals. Yeah, I guess we could even do the hackish way. We can say heap Oh no, we can't, because we first gotta pack those into uints. So let me actually do a different loop. Which will be a bit slower, but this doesn't matter. We loop from 0 to size over 4. So we know that if we enter this loop at all, we have at least 4 characters. Alright. And then we say heap of heap size, which is the current top of the heap, equals string plus I or with string plus I plus 1 shifted up by 8. Alt width string plus I plus 2, shifted up by 16. Alt width well, more like this actually. This we shift up by 24. And this should give us the right the right results. At least on little endian architectures. No, think on every architecture. Yeah, because they're bite-sized. And then, in case just in case we did not cleanly divide by 4, we need to put the remainder there. So we switch on this. We could call it rest or remainder rest. We switch on this, and there are only 3 possible values. Either we had 1 too much, we had 2 too much, or we had 3 too much. Alright? In case where we just had 1 too much, we say this plus size over 4, and heap of heap size equals that. And of course we need to post increment the heap size. Which means we do not need to do this. Yeah, actually it does make sense to do those in the opposite order, because then we can merely fall through. And this expression is used rather often, so we just say auto size over 4 equals that. And then we can use size over 4 can basically make this an enum if we want to. Now let's make it an immutable. So it will be a variable. We can basically use it here. If of heap size plus plus equals basically that. Yeah, and we need to make sure that we dereference that string in every case. This is what we want to do. And just for symmetrical reasons, we do like that. Okay. This is what we do if we have case 3. This is not I, this is size over 4. Yeah, so this should be correct. And we mustn't forget that there is no implicit fall through in D. And we just do that. Oh, and I guess we actually can and should act on 0. Well, I'm not sure. We will see later when we run this. Yeah, maybe we should just switch on size by 4. Could also say and 3. This is the same as modulo 4. Okay, 0. Whoops. Yeah, I guess that would change when we remove one level of indentation. In that case, it would just take size over 4 and shift it by nothing. And of course we need to make sure that we the heap of heap size and equals that. And here we do have to heap size plus plus. And this should copy the string accurately. But in the case where the size of the string is 0, we need to do an additional advance. And this has to go to case 0. In order to make sure that the terminating 0 is preserved, we have to advance the heap size in case this were 3. Yes. So let's just do that. If size 3 equals 3, we have to do heap size plus plus. Yes, this should work. Let us actually have a side buffer that tells us which types of things are on the heap. This will make debugging easier. We have a struct called heap entry that has the BC type enum, or the BC type, the type of the entry, and and the size of the entry. And we have a heap entry array. Heap entry array. Entries. And on push string we do entries concatenate equals heap entry. Maybe we should do start address. Just because this is just for debug purposes, we might as well stuff every bit of information in there we can. This is the current heap size. And the type is BC type of BC type enum dot string, and the type index is 0, and we actually know the size of it. The size is size. This should, in theory, make sure that we can view our heap nicely. Well, let's check if we can push a string on our heap. Yeah. Let's go on our CTFE BC file. Let's go to string expression. And let's do it like this. Let's call push string CTFE, whoops, CTFE, shared CTFE state dot heap dot push string se dot string, which is a castra, and then the size, which is se dot len. Alright, and they should push on our string. And what do we get back from there? I hope it returns the heap address. It does. But the return statement isn't there. That's easy. Heap address of heap size, and then at the end we return the heap side. Not the heap side, the result. And that should give us our heap address. And push on the string. Okay. Let's see if we compile. Okay, I missed parentheses. And the brace. And something else. Though at the moment I don't know what. A different file. Probably somewhere in the CTFE state. Yeah, 141. Oh, I missed a semicolon here. And I defined the heap in the wrong file. Typical. Okay, I have to use a final switch. And I have to cast the size to uint. So first let's do this cast. This means I just hope that you never use strings that are bigger than 4 billion. And here we have to do a final switch. Alright. This means we can push on the string. And now we will not store this stuff on the array anymore. On the stack anymore, which means that we won't have all those set thingies when we print our instructions. And yeah, we see that we don't have all those set thingies when we print our instructions. We just get an assertion failure right away in BC Common. Alright, 144. Presumably this is the one where we check that we are zero terminated. Yes. And of course we have to assert that it is 0, not that it is not 0, right? Yes. Now it should look different. And we have an assertion failure somewhere else. In 737. Six, 737 is the one where we assert that we didn't give up when doing stuff. We can comment this one out, rebuild it, and now we should build, and it should go into our bytecode CTFE evaluation path, but it will see that we gave up and will use the normal one. And you will see that we don't consume so much stack space, or stack usage is 16 byte because the string is no longer pushed on the stack, which is good. Alright, this concludes our the heap part of things. I think we have this string now nicely on our heap. Yes. Perhaps we should assert that we do. Yes, I think so. Debug CTFE. Right then. What we want to write out is the size. Then the result dot address. Did I call it address? Yeah, I guess I did. And then the result address minus the heap size we have currently, and that should be the size over 4. Then the size over 4 after that. And we should see the same value in those two. Oh, almost the same value. Oh yeah, and we need to import std, of course. And now we should see almost the same value with one difference in case where the string was bigger than we allocated for. Yeah, so it's here. this here is where we allocated so much stack space before, but no we don't. Size is 32, size over 4 is 8, and I guess we phrased the subtraction wrong. The heap size will be the bigger one, and we need to subtract the old heap size, which is the address where we pushed it. And this should be 8 or 9, I think 9. Let's check. Yeah, it is 9. Which is perfectly fine. This is exactly what it should be. Alright, with that I am going to save the recording and load it up to YouTube, and maybe later today we will go into actual concatenation. But for now we introduced the heap and made a way to push strings on the heap. And I think that's quite an achievement. Alright, see you next time.